In the next example, we'll be graphing to determine whether or not the function is one-to-one to begin with. And then if it's not, we'll need to restrict that domain to make it one-to-one so we can find its inverse. So let's first graph this equation here. Notice it's in vertex form with an A of 1, so there's no stretching or compressing. So that means that we have a vertex of 3, -1, so we can graph that over here, 3, -1. Since there's no stretch or compress, it has the same format as a standard parabola. But if you're not quite sure how that works, you can still plug in some values for X and Y. If we go to the right, let's say we plug in 4 and 5. If we plug in 4 into the equation, that's going to give us a 0. So 4 is 0. So if you remember the axis of symmetry, if you have the point at 4, 0, then there's a mirror image just on the other side of that axis of symmetry. If we plugged in a 5 into the function up above, that would give us a 2 squared, which is 4. 4 minus 1 would give us a 3. So we have the point 5, 3, and another point across here on the mirror image. So this is what the graph would look like. Now, even though this is a function, it is not one-to-one. We can tell because if we were to pass a horizontal line through that graph, it hits the graph at more than one point. So that means we need to restrict the domain in order to make it one-to-one. So in order to restrict this domain, we probably want to start at the vertex so we can get as much of this graph as we possibly can. So we will restrict the domain to where X is greater than or equal to 3. In interval notation, that would be 3 to infinity. So that means we would only take a look at this part here to the right. That part of the graph would be one-to-one. So if we're asked to find F inverse of X, and again, let's recall that F of X is X minus 3 quantity squared minus 1, where X is greater than or equal to 3. We've restricted the domain, so it's one-to-one. We're going to use the fact that if one function has AB, its inverse would have BA. So the first thing I want you to do is replace that F of X with a Y. So we have 2 variables that we can work with. Now, let's switch that X and Y. That gives us X equals the quantity Y minus 3 squared minus 1. Now, solve for Y. Keep in mind, we're wanting to get Y by itself. So we're going to take the square root of both sides. And then add 3 to both sides. So this actually gives us our inverse function of 3 plus the square root of X plus 1. Now they're wanting us to graph F and F inverse on the same set of axes. So again, F of X is X minus 3 quantity squared minus 1. F inverse of X, and here's where X is greater than or equal to 3, where the inverse of X we found to be 3 plus the square root of X plus 1. Now, as you recall, we restricted the domain for F of X, which means the domain for F inverse will probably be restricted as well. Well, if you remember how to find the domain of a square root, we know that that X plus 1 has to be 0 or larger. In other words, it has to be positive. So just by the nature of this function, we know that this X value has to be greater than or equal to -1. We put in -2, then we're taking the square root of a negative number, and we're only dealing with the real number system, so we can't do that. So one of the things I want you guys to note, Just as if f of x has the point AB, the inverse has BA, that also works for their domain and range. So for example, let's go ahead and graph f of x again, but on that restricted domain. Remember, it's that right side of the parabola. So we had a vertex at 3, -1, and a point at 4, 0, and at 5, 3. Okay, so that's f of x. So for f, it had a domain where x was greater than or equal to 3, but it also had a range. Notice the y values start at -1 and go to infinity. So the range is y has to be greater than or equal to -1. So guess what? When we look at the inverse, okay, that inverse function, its domain is x is greater than or equal to -1. So guess where our range is going to start? Everything flips, right? So our range value of y is going to be greater than or equal to 3. Kind of cool, right? Let's choose some values for the f inverse. We've already graphed f. So if we have x values and f inverse values, remember, if one has the point AB, the other one has the point BA. And also, I want that square root to come out to be a nice, perfect square. So let's choose some numbers wisely. For example, let's plug in a -1 in for this x up here. -1 and 1 gives us 0. So we get the point -1, 3. Yay. If we plug in the point 0 for x, we get the square root of 1, which is 1. So 3 + 1 is 4. We get the 0.04. And last but not least, if we plugged in the point 3 in for x, that would give us the square root of 4, which is 2. 3 + 2 is 5. So we get the 0.35. All of those points are opposites of the points that we get for f of x. They're switched. So if we take a look at this graph here, and we were to graph the line, I'll just graph the line through here, of y equals x, that line just splits the first and third quadrant right in half. So notice how these two graphs are kind of mirror images of each other across that line. So that's how we can kind of take a look at the functions. Did I have to do this table to graph f inverse? No. I could have taken the entire table, all the points of the f of x function, which was 3, -1, 4, 0, 5, 3, and I could have just switched them around. But it's always nice to verify that the function that you got does in fact give you those points back.